for our voice.
I think, yes, we said yes, right.
Yeah, we don't use this camera.
Yes, the camera here, it will follow you.
Oh, I see. Right.
Just make sure you don't trick by the
Oh, yeah,
cables right
be
here.
careful. Thank you.
Yeah, we said.
Yeah.
Yeah.
Thanks.
Thanks,
All right.
Patrick. I will do the intro.
Okay.
Yeah, probably 4 or 5 minutes.
Yeah.
Every flight. Oh, man. It's not a course. No credit.
Oh, there's no camera.
Yeah.
Is there two?
No, no,
Is it Zoom?
We don't-
Just audio?
It uses that.
I do not.
Yes, I would be like, he was sitting behind.
So yeah, so we have 3 weeks. And we have now like 16 every year. We get like so they are.
You know, you watch the game. Like literally.
And what is that?
My statement was if other
Sounds like
person,
he's blaming me for your.
her statement was if other person.
I was gonna watch on the.
Oh, yeah.
This will be fun. This will be the last one and I'm just going to regret. Which one?
No, that's a cat.
It's like a 3D weird.
Well, they never use it.
Well, you don't know, so you're not. It's like the camera.
Well, connected to the computer to-
Always the best experience, like 45, 50 days. That's the best you can do.
Can't believe you didn't come for icon today. Nice. Must be watching it and laugh.
This is that was here.
All right, thank you everyone for coming. My name is Wang. I'm a Icon seminar organizer and also assistant professor here at Purdue Sim Engineering. Today is really our pleasure to welcome Professor Junmin Wang from UT Austin. Professor Wang is currently an endowed chair at UT Austin's Department of Mechanical Engineering. He actually spent 8 years before moving to UT Austin in 2018. He spent 8 years in Ohio State, where he was actually promoted from assistant professor to a full professor within 8 years. That's the dream of every young faculty like me, that we dream of, that we can get promoted to the full professor within 8 years. And now he has been doing a lot of great research in control dynamics, AI-assisted vehicle motion planning, and all those and cyber physical system and things like that, where Professor Wang will introduce. He has published more than 400 papers and 13 US patents. He also has 5 years of industry experience at Southwest Research Institute. And you don't see a lot that a professor has fellowship across all those 3 different domains, ASME, SAE, and IEEE fellow. So it's really our pleasure to have Professor Wang here, and let's welcome him.
Thank you very much, Professor Wang, for the kind of words and introduction. My great pleasure to visit Purdue here
As Professor Wang mentioned, I was a neighbor of you several years ago, but I never had a chance to come to campus. This is very exciting for me. I met with many of your very talented faculty members and also students earlier today, and I was really, really impressed. So today I hope to cover some of our work in past several years regarding this personalized automation or personalized control for applications in the ground transportation domain. So okay, let me see, can advance. Okay, let me see something. E-commerce side. Okay, that's a trick. Oh, there we go. Thank you. So little outline, perhaps not everybody is in this domain, so I will briefly introduce connectivity, automation, and maybe intelligent ground vehicles. Then I want to spend the majority of my time on two aspects. One is how can we use learning and personalization to improve operational energy efficiency. Secondly is that whether we can do something to improve the driving safety. And finally, some conclusions. So I like to start almost all my talks with this big picture. So what is the impact, right? Why we do this ground transportation, ground vehicles, why it is relevant? So from several aspects, first is energy consumption. If you see this plot, x-axis is calendar year, y-axis is the big unit number. This basically tells us in the nation, in the US, what are the major sectors in terms of energy consumers, right? So you can see that number one is green, which is industrial, and the number two is transportation. That is the blue section. So this vertical line means 2020. That means on the other side, those are historical actual data. On the right-hand side, that model predicted data. You can see still transportation can continue to be the number two energy consumer across all sectors. If we take a closer look in terms of energy consumption in the transportation, which include not just ground transportation, but also air, marine vessels, all these things, right? We can see now the highest consumers are the dark blue and the light blue. Those are diesel, it's light duty vehicles, medium duty vehicles, etc., right? Heavy duty trucks. So they are the majority of the transportation energy consumers, right? Air, which is green, right? Rail is this purple, and then we have marine, right? So they are much smaller compared with the ground transportation. That is why the energy consumption, energy efficiency is important. And another aspect on this chart, we show again, x-axis is calendar year, y-axis is energy unit. Again, we can see the brown and this light brown. Those are the two major energy sources for transportation. They are gasoline and diesel fuels, right? So you can see even in the next 20, 30 years, predicted by the DOE models, majority of the vehicles on the ground transportation is still powered by diesel and gasoline petroleum fuels. Electricity is yellow, that is increasing, but still the percentage-wise is quite small, right? So we have a lot of work to do. You can see the two dips here, right? This dip and this dip. Perhaps you can guess the reason, right? That is due to the COVID years, right? Our reduction in terms of mobility. Another aspect is air pollution, the environmental impact. So I sampled this data, which is from the EPA 2023 data. In the country, you can see in terms of NOx, right, which is a harmful species, who are the major contributors, right? You can see here blue, that is industrial and residential. However, this green, which is a mobile air, that means airplanes, right? This yellow, which is a marine mobility, and brown, this part, ground transportation, right? A very big portion of the NOx emission contribution. Safety, also critical. This chart shows the historical data in the nation by Department of Transportation. X-axis, again, calendar year. The y-axis is number of people being killed on the road, right? Every year. You can see when we are 1970s, every year we have about 44,000 people being killed, not injury, right? Not injury number will be much, much higher. Just this is fatality, right? So it's significant. It's a little bit depressing. We look at the recent year, right? Still 42,000 people being killed every year in the country. So there's not much of a reduction. However, if you look at this data from another aspect, that means this black line, which is essentially the fatality rate per 100 million miles of drive. And this curve is encouraging. In general, it is decreasing, right? Because as we having more and more vehicles on the road, as people driving longer and longer distance, we were able to keep this fatality rate coming down, negative slope, right? Mostly. But recent years, we have some, wrong direction going on, right? So that means we still have a lot of work to do. But this largely, the negativity of this curve is due to the technology advancements, right? So seat belt, ABS, right? All this airbag, EPS, all those AEB, or ADAS, right? The keeping system, all those are contributing the decreasing of this curve. Looking into the future, we are in a smart, age. So we have smart cities, smart living. People can do many things remotely, right? During the COVID years, we can remote learning, remote shopping, remote healthcare, etc. Seems like we could do everything online, everything remote. However, one thing we cannot do remotely is we need somebody and something to transport goods or people from point A to point B, right? That is our ground mobility. So in these four important aspects of our society, ground mobility, ground vehicles play a very critical role, right? So I always try to say that any improvement here will have a very big impact to our society because the huge number, right? The volume is very high, right? 3% increase, 5% increase, multiplied by a huge number of vehicles, we're going to have a very substantial impact to our society from energy, environmental aspect, and even safety, right, perspective. So the background here with that is the technology advance. One is this increasing level of automation, right? SAE has this roadmap, try to characterize the vehicle automation into these 5 levels, or actually 6, right? So essentially level 0 is nothing is being automated, everything is done by the human driver, all the way to level 5, that means human will be doing nothing, everything is done by the machine, right? In between them, we have different levels of automation, right? Increasing level of automation. So that is right now on the market, perhaps we are somewhere here, right, in the middle. Many of you, if you recently bought a car, you actually probably will be level 2, right? You have the keeping system and adaptive cruise control. Those two together are considered as a level 2 automation. Another is communication. So with this, wireless technology being advanced so much, we almost can exchange information between vehicle and almost everything else, right? To the human, to other vehicles, to the cloud, to infrastructure, almost everything else. So essentially, this brings us to a new era in which we have unprecedented information richness and the new degrees of freedom due to automation, right? So the question here is that we are looking beyond just automated driving. What we are interested in is how can we substantially improve, for example, a vehicle energy efficiency, driving safety, human trust, human acceptance by leveraging those information richness and also automation functions. So essentially, we want to leverage our deep understanding on these physical systems, plus the availability of information and the degrees of freedom, providing new degrees of freedom, leverage our infrastructure, really create some synergies, right? That synergies can be impact positively our society in terms of, all those energy, living environment, and also safety. So in this background, even though we are having increasing automation, however, humans are becoming more and more significant in terms of the vehicle safety, efficiency, and automation, including human driver style variation, human characteristic changes, and human capability differences, right? Those are becoming more and more important. For instance, more than 90% of the crashes on the road were caused by human errors right now in the modern society. Different human driving styles can cause up to 40% efficiency difference, right? And up to 40% tailpipe emission differences, right? Everything else is same. Just change to a different driver, we can have up to 40% variations, which is huge. And we're gonna already having this human-driven and automated vehicle collaborating, sharing the road together in mixed traffic, right? So another aspect is trust, human trust in, and also humans' acceptance of automation, which is becoming more and more critical and more and more important to address. Looking into the future, perhaps we will not have driverless cars. We're gonna have human drivers or machine drivers or combination, right? Human / machine drivers. And in this context, there are several aspects. One is that a recent study survey conducted by the Institution of Insurance Companies several years ago, what they did was they surveyed 1,000 new cars, right? They essentially, these 1,000 new cars, different customers bought those new cars. After they use these new cars for about 3 months, right? Or maybe half a year, typically you will return your car back to the dealer to do the first time service of the car. What they did is that check those automation function, whether they are enabled or disabled, right? At the first time returning back to the dealer. Guess the result? More than 50% those functions were disabled purposely by their human users. That means our engineers design all these fancy automation functions, but in reality, we are not that accepted by the human users, right? When they are not using it, they are not accepting all these benefits we engineers, designed for, nothing, zero, right? No impact. That's one thing. Second aspect is this, right? Humans tend to be more demanding on machine drivers, right? So I don't, maybe, many of you had somebody to give you a ride, right? Some riding experience, right? Could it be an Uber driver, or could it be your partners or friends, right? For example, sometimes my wife, gives me a ride, right? Often I will have a lot of complaints about how she's driving, but I keep those complaints inside. But otherwise, I'll be in a bigger trouble. I keep those complaints inside. But if it's a machine, I will have a lot of complaints, and I will, throw them out, right? Because it's a product I bought, right? So I paid money that product to serve me, right? And I'm different. You are different from me, right? Everybody else is different from others, right? So that is very important. That is kind of one of the motivations we want to do the personalized automation and personalized control. So why this is necessary? So if you look at data, let's say a single popular passenger car, like some of the Toyota models, they can reach to 300,000 units in sale, which means we have over 300,000 different humans operating the same physical system in all over the world, right? Different locations, different weather, different climate conditions, and different human habits. Obviously, this is a suboptimal combination. So if we can leverage our daily operational data from this driver vehicle pair, right, individual pairs, then learn from this usage, right? Try to study the human user individually, and then do this personalization of the control we might gain some benefits, right? Benefits in terms of efficiency, benefits in terms of safety, and also benefits of increasing the trust of human users to this automation, right? So those are all possible. However, we have to do this by learning from individual users, right? The OEMs like Toyota cannot do this because they don't know who is going to buy this car and where this car is going to be used and how this car is being used, right? We can only do this during the usage, right? Learning and then adapt. So how do we do this? So the central piece here is the modeling and the prediction of individual humans, right? Using the data, using the historical daily data, try to characterize the human's preference, skills, characteristics, right? Also, like emergency behavior, driving style, frequent routes, and all those things. Then on one side, we can leverage this knowledge to personalize our, for example, motion control, right? How do we accelerate? How do we steer? How do we maneuver, right? To increase the human trust and acceptance, thereby increase the driving safety. On another side, we could leverage this information to predict and to enhance the optimal control of the propulsion system to increase energy efficiency and reduce tailpipe emissions. So in my, again, creating synergy among these three pillars. So my lab has, in recent years, we invested a lot of resources to develop this integrated human vehicle automation simulation platform. So the centerpiece, this is a real-time simulator. And then we have this very high-end immersive driving simulator, human subject can be in on the motion base. Then we can create this virtual reality environment. We can also simultaneously measure human brain activity, muscle activity, human cognitive activity like gaze motion, eye tracking, etc. We also can implement various controller algorithms, right? All of this can be integrated so we can learn, adapt, and also evaluate, right? So this is a whole loop. And also the simulator capable, I show you two more examples, videos. One is we can also simulate automated driving. So now in this case, we don't have a human driver on it. We can program it to automatically steer, automatically deal with other traffic participants. For example, there is a coming stop sign here. It will be able to recognize the stop, then make a left turn. We can also simulate the different weather conditions. I don't know if people on Zoom can see this. Actually, you can closely see the raindrops, right? We can simulate the weather condition, raindrops, deal with other vehicles, but all those are possible, which is really a powerful system to help us to put the human into this like a movie theater setup and to be very immersive to study human and automation. Okay, now let's get into several examples. First is how do we do this propulsion control, right? Personalized propulsion control. I give you one example. This is a hybrid electric propulsion system. Basically, it has an internal combustion engine. And in parallel, we have electric drive, right, with motor and the battery. So all these together try to essentially, we want to minimize energy consumption, also minimize tailpipe emission, right? As this diagram already trying to show, this is quite complex physical system, multivariable, nonlinear, all these things. But meanwhile, it also is constrained system, right? We have all kinds of physical constraints. So as all of you probably is in this domain, we know in order to do optimal control for this constrained complex dynamic system, we need to have future information, right? The future reference information. Where are we going, right? What are we asking the system to do in the future? Once we have that, we can do optimization, right? Optimal control. Okay, so we have, like connectivity, all this camera, LiDAR, radar sensor, right? We can have future traffic, future road information available right, from those perception systems. Even though the system is stochastic, but still we can detect them, right? However, from this traffic loading information to the future reference signals of the propulsion system, which is the future torque and speed demand, in between, there is an uncertain element, which is a human driver. Everything else is same load, same traffic, different humans will translate this information to different torque speed demands, right? And this piece is very uncertain, right? Unless we can solve this have a good way to deal with this uncertainty, it's very hard to achieve optimal control in the real world operation. So how do we address this? Let's first look at this example. Essentially, is a HEV energy management system on fixed route driving. So what is fixed route? Fixed route driving actually is very common. For example, our public buses, right? Utility vehicles, like garbage collection trucks, right? Commuter vehicles, even our personal cars, they actually often drive on fixed route. If you think about you drive from your apartment or from your home to school, most of the time it goes through the same route, right? That's called a fixed route. So even though the route is fixed, it is different from the so-called fixed cycle driving. Fixed cycle means the vehicle speed is a predefined function of time, right, that is used to standard testing for vehicle efficiency, emissions, etc. Fixed route means, okay, I start from point A to point B, I go through the same route, but every trip is different because every trip we have different traffic, different weather, different vehicle condition, or different human mood, right? So this is a completely, it's a stochastic process, even though the route is fixed, right? So that's the nature. So how can we better utilize the electric power and engine power to improve the energy efficiency of this HEV on the fixed route driving? Right? So that's a problem we addressed several years ago. So we started with a typical fixed route, like a 12-kilometer route, which had 8-kilometer local drive, 3.5-kilometer highway, some uphill, some downhills, left turn, right turn, stop signs, and also traffic lights, right? Graphically, something like this, right? It's a little bit representative of a typical home to work kind of route. So we did 24 trips by a human driver. And if we look at the overall, these 24 trips, you can see, oh, the average, if we do average, right? Just average all the 24 trips, we say, we found, okay, average travel time is about less than 14 minutes. Average speed on local is 15. Average speed on highway was 96. And average number of stops was 14.7 because we have traffic lights. Sometimes it's green, sometimes it's red. So if we only look at average data, it doesn't tell us, much information. So then we took a closer look. So we found a segment of the data. So we look at this segment, which is about 50 seconds of driving, and we have 10 different trips, right? We plot this data. So the x-axis, for example, first plot is time in seconds. The y-axis is the vehicle speed. We found we have clearly two groups, which is the blue group and also the pink group. For the blue group, they didn't stop, right? For the pink group, they all stopped, right? So we call it non-stopping and stopping groups. Now further, we plot the same data in the distance domain, right? Just change the x-coordinate to be the distance. Now we found for the stopping group, all of them stopped at almost the same location, right? Which is here. Then we go back, then we went back to our route. We identify, okay, this particular location was a stop sign. That means for the blue group, they were lucky, they had green light, pass through, no stop. And for the pink group, they had red light, so they have to stop. But the duration of stopping are different, right? Time to time, it depends on which phase of the traffic light we get in. Here is the pedal position, right? And for the stop in both time domain and in the distance domain, right? So one thing here we note was inspiring was when we put the data in the time domain was less informative. When we put the data in the distance domain, it's kind of a little bit more informative, right? So that was kind of inspiring. Then we also compared these two groups, stopping and non-stopping group. We found that a very different kind of data set is this regenerative braking energy. That means because this is HEV, it has electric motor. When you brake, the motor can switch to a generator. It can convert of kinetic energy back to electricity, right? So we can obviously see this stopping group. They had much higher regenerative braking energy being generated or being captured compared with this blue group, right? So that is kind of inspiring, saying, okay, this might be something useful that we could leverage to increase the operational energy efficiency. So we use that inspiration. We divided this fixed route into smaller segments by using these deterministic road and traffic features. Because for that example, we know where the traffic light was located, right? But meanwhile, we also know the location of stop sign. We also know the location of sharp turns, location of uphill, location of speed limit change, right? Even though this entire trip is stochastic, but along it, we have some deterministic information. If we use those, we might be able to improve our speed and power prediction and increase the efficiency of learning from the driving data, and ultimately can help us predict the human's behavior. Then subsequently, we can do better job in terms of energy management. So that's what we did. We essentially use these deterministic features to divide one given route into smaller segments. Then within each of these segments, we do the learning and do the optimization, right? Because this is helpful. For example, this is stop sign number 11. So we know, depends on direction of travel. If we're going this way, we know the vehicle speed most likely going to be 0 at this location, around this location, right? So that is very helpful for the prediction. Same as here, right? We know this is going to be a sharp turn, most likely going to reduce its speed. Otherwise, the vehicle will get out of the track. So essentially, we separate this energy management system into two portions. One is offline learning and optimization. Secondly is online real-time implementation. So I'm going to explain a little bit on both sides, right? One thing here is that using the historical data, we can collect every trip, put them in the cloud, then we can do this offline optimization, produce the learning-based optimization result to inform the online controller how to do this power management when we come to each of these road segments. So we created this road segment-based stochastic model. So essentially, for any of this case road segment from the previous historical trip, we consider these two variables. One is the battery state of charge change and the engine fuel consumption as the two variables of interest. For all future trips, we consider these two as random variables. Then as we accumulate sufficient number of trips on this fixed route by this vehicle, by this driver, we can create their occurrence frequency, then we can come up with a probability distribution of these two variables. Then we can have the stochastic model in terms of energy consumption. All this can be done online. So this is example, right? Some of the energy consumption characteristics with different lambda. So lambda here is the control parameter, right? Lambda decide the variable between 0 and 1. So decide how much we should use engine, how much we should use electric drive, right? So essentially it's a power split ratio. So this is we use a stochastic dynamic programming offline, right? So running cost, terminal cost, then we do the backward indication, backward induction, then we can come up with this optimal control policy. At the end, this offline learning and optimization result can be summarized as a three-dimensional map. So this three-dimensional map, as exemplified here on this plot, we have two inputs. One is the a segment index, right? Row segment, which segment we are about to enter. And second input is that at this moment, what is the state of charge of the battery? From these two, then we come up with the output, which is a lambda, which is a power stability ratio, right, for the HEV to use. So you can see, even though the learning and optimization is pretty lengthy, but the end result can be summarized as a three-dimensional table or map stored in the memory of the car. Memory is nothing, right? It's onboard wise. Then we can use in real time, right? So no computation, just table lookup. So we compared this with three other methods, right? One is point-wise DP. That means we do this backward conduction calculation after we finish. Every meter go back, right, to see what would be the best possibility, right? Obviously, this is not casual. This cannot be implemented, but this is a benchmark, right? Second approach is that this is a segment-based DP. That means we don't do the point, but we do segment, right? And third is this rule-based charge deplete, charge sustaining strategy. So make a comparison, we can see, okay, the PDP that is absolutely and theoretical optimal. Compared with other two methods, we only increased less than 2%. That means compared with CDCS, which is a real-time implementable EMS, energy management strategy, we can reduce by 7% energy consumption. Right? No hardware change, just software. And as we mentioned at the beginning, right, 7% energy consumption reduction, which is huge. Because when we are achieving the 7% on average, right, because it's a stochastic process, we cannot guarantee every chip give you 7%. But over a month or two, average expected value is about 7% without affecting any driver. Right? This is underneath, right? Without affecting driver's preference, without affecting your demands for speed, right? Your pleasure of driving, no effects on this, right? So this is good. All right, let's switch gear. On the safety side, so this is another aspect we found is that humans, we all have different control characteristics in terms of steering. For example, we asked the three human subjects. Here we are labeled them like driver 7, driver 8, driver 10. We asked them to do a standard lane changing maneuver. We found them, all these three humans, right, exhibited differences in terms of their path, in terms of the way of doing the lane changing maneuver, right? So that is very obvious. And then we have, okay, whether we can come up with a model as simple enough, but capture those differences in terms of human steering behavior, right? Human steering characteristics. And we also want to keep the model analytical. We don't want to have machine learning model because we want to use this model as a next step in our active steering control, in our assistive control, right? So this, we envision this would be part of our control model. So we had about 7 and 8 parameters. And then once we have this model, all we can need to do is that, okay, this driver is driving this car, making a lot of steerings, making a lot of lane changes, right? We record all this historical data. Then we do offline calibration of this model parameter. So we can come up with a set of parameters for this particular driver when he or she is driving this car. And then the model can very well match with the human's steering action. So we show you here driver 5 and driver 8, right? Doing a lane change maneuver at a very high speed, 75 mph. You can see comparison, right, between the model predicted value signal and the actually measured signal of the steering angles. They match pretty well. Driver 3 and driver 8 do a double lane changing maneuver on highway, 55 mph. That means you switch lane, then you switch back, right? It's kind of collision avoidance maneuver. We also can very reasonably, very well, the model can match with individual humans, right? One thing you can also see that among this, on this slide, we show driver 3, 8, and 5. All these 3 humans, their steering behaviors are different. You can see between these two, right? As same is here. Our steering behavior is very different, right? From human to human. But you may say, this is nothing, right? Okay, you have model, you have data, you run optimization, right? You have a good set of parameters, right? That's you do every day, right? So what's the meaning? The actual power of this work, which was done in another paper, is prediction from ordinary maneuver to collision avoidance maneuver. So you can think in this shared human-machine driving, the driver model must predict an individual's steering signal, steering command in collision avoidance situation, right? Because the human steering command may or may not be successful in terms of avoiding collision, right? So if the model can predict that behavior, then the controller, which is working in parallel with the human, can be better informed about, oh, my human is doing this. I can compensate accordingly, right? Compensate in a tailored way, in a personalized way, to team up together, make it successful, right? However, these things, they will need to be used during collision avoidance maneuvers, but we don't have collision avoidance data, right? Because collision avoidance does not occur frequently, right? Maybe all of you are very good driver. You may never had a collision avoidance situation, right? For me, I'm a bad driver. Occasionally, I have 1 or 2 times a year, right? That's about it, right? We don't have data to learn that. So that's a challenge. So what we did was, interestingly enough, if we dig into these ordinary steering maneuvers deep enough, we found there was a way we can correlate the characteristics of these ordinary steering maneuvers that we do every day to predict the individual human's steering model parameters when this human will be doing emergency collision avoidance handling or maneuver. And by using these predicted parameter values, we can predict his or her steering signals reasonably accurate, which can enable our controller to do proactive control, right? So I show you a couple of examples. So this one is driver number 4 and driver number 11. I try to show you different humans, right, in our study. You can see this is lane changing maneuver, right? The 2 steering signals, right? Driver 3, driver 7. Also, colors, blue and green, right? They are different behavior. In parallel, in the collision avoidance, you can see the same drivers, like number 4, which is black, number 4 here. You can see the black curve here are very different. Right, number 11, red here is very different. Right, bottom is same, right? Blue to blue, green to green are very different. That means different, same human, ordinary steering, collision avoidance, their steering behavior dramatically different, right? That's why we have to predict. Right? We cannot use the same parameter for the ordinary maneuver for the emergency handling. This plot is more interesting. So we summarize all the 20 human subjects we studied, right? Different age, different gender, different years of driving experience. So this one shows you just 4 of the 8 parameters, right? For example, this is a G sub H, that's a steering gain. T sub H, that's a delay term. L is a prediction distance. K sub FF, that's a feed forward gain. So you can see across these 20 human subjects, first of all, we are showing 2 colors, right? 2 bars. One is the gray, that is the highway lane changing maneuver, which is the ordinary maneuver. Black, that's highway collision avoidance, that's an emergency maneuver, right? You can see, for example, GH, for the same human driver, black and the gray bars are very different, right? Some humans have similar ones, right? For example, number 12, black and gray are almost the same. But also you can see the parameters across these 20 subjects are variables, right? They are different. However, universally is this one, KFF. You can see for everybody we tested, their black bar value is much, much higher than the gray bar values. So what does this mean? This means when we are doing this ordinary lane changing maneuver, we do not use feed forward. because our feed-forward gain, which is gray, which is a very small value. That means we are doing ordinary link change maneuver. We have time. There's no emergency. We check our lateral error, check our distance, right, relative speed. Then we adjust our steering, right? Most likely a feedback process. Therefore, the feed-forward component, feed-forward gain is very small. But come to the collision avoidance, everybody the black bar jumped up like 10 times, 20 times higher. That means in emergency handling, most of the humans will rely on feed-forward control. We have no time to check error. We have no time to calculate distance. We just issue the steering command from our brain, from our experience. Whether this steering command is going to be successful or not, that's a question, right? Some may not. So we have this model. Now, next step is how do we use it, right? So we can do this driver-centric automatic steering control. So there are two kind of categories in doing this. One is called automation centric methodology. That means they control, the controller control the vehicle motion, right, based on this road vehicle dynamic model. And they treat the human driver's input as a disturbance, right? You can do robust control, you can do disturbance rejection, they do this motion control, right? Another category of approach is that driver-centric. That means we can provide control action from an integrated model, including driver, road, vehicle altogether. Therefore, we can offer this collaborative action, right? By taking the human driver into the consideration in a personalized way, right? So that's what we call it the driver-centric. In this aspect, we conducted two different treatments. One is using this our robust control, right? Robust personalized control based on the analytical driver model, like the one we just showed, right? Second approach, if I have time, I want to introduce is this adaptive personalized control based on a neural network driver steering model. So the first one is pretty more straightforward. Essentially, what we did was we augmented the model to incorporate this driver steering model that we learned, analytical model with the parameters being learned from the historical data as part of our metrics, system metrics. Then the controller will be dealing with this integrated vehicle. This is the vehicle corner, right, with the vehicle model, vehicle parameter, and human together. Right? So the controller is not just dealing with vehicle itself, but also considering human naturally as part of the planet, because we learned from data already. Then we can do a H infinity controller, gain scheduling, etc. So I want to show you two humans. One is called A2, which is blue, that is an inexperienced driver. Second is B2, which is red, that is an experienced driver. From their historical data, we learned their driver parameters as listed here in the table. You can see the values are different, right? So the values, these are same, but this is very different, right? Because of their skill levels are different. So we asked them to do this double lane change maneuver, right? Like clearing avoidance, right? So here is an obstacle, but here is also another upcoming obstacle. You have to steer to the left and come back, right? It's a very challenging maneuver. So we can see this A2 and P2, right? For example, this blue and the green. So blue is here, that is inexperienced driver with the personalized controller. It can successfully finish the maneuver. If we don't have control, this driver will fail. Right? This you can see is already 10 meters lateral displacement, basically out of the road already, right? Spin out. For the B2, which is the experienced red and this dotted red, you can see not much of difference, right, between, because this is already a very experienced driver by him or herself. It is already successful, right, without much help. And more detailed information, this is, for example, vehicle yaw rate. This is the vehicle lateral acceleration. You can see compare this with and without control between these two different human drivers. First of all, you can see these blue arrows, the lengths indicate the difference between the controller being active and without the control, right? You can see for the A2 driver, which is inexperienced, the difference is huge. That means the controller provides a lot of help, a lot of assistance. But for the B2 driver, you can see the difference in this red. It's very short, right? That means the controller provided the minimum help, right? So that's a personalization, right? Because otherwise, some of you, I guess, you may be experienced driver. I guess some of you may be racing car drivers, right? When you do that, if you see the racing car drivers, they never use automation, right? Because if they have automation, it will be disturbing them, right? So that is this is about, right? So that is a personalization by the same controller. Next, okay, I want to cover this one. That's one thing. But the question here was, oh, we rely on this assumption that we have this analytical model of the driver steering behavior learned from the data. However, you might say, okay, this learned model may have uncertainties, right? Or they may not be sufficiently capture the human's steering behavior, or a same human, their steering behavior may change day to day, right? Those are all reasonable arguments, right? I'm not denying any of them. So that's why we started another approach, which is following the neural network to whether we can help. So this one is, again, using this road vehicle model, right? So I can skip these details here. The key thing is that, okay, instead of using analytical model, let's use a neural network. And use this neural network to mimic and to learn the human's driving steering behavior, right? So you can see after learning from data, training this neural network, we were able to reasonably, this is a steering command, right, from the human, mimic the human driving steering behavior, right? The question here is, okay, you have a neural network-based model for steering, and you have data, you train the model, you calibrate the parameters, you calculate the performance, right? That's everybody's doing right now, right? Everybody's doing this. How do we put this in controller? How do we take that neural network trained model into our controller, analytical controller with guaranteed performance, with guaranteed stability properties, right? So that's what we want. So here, now we consider this shared control, right, with two human steering and then controller steering, right? Add it together, become our front wheel steering. So in this, we combine the road vehicle model and the neural network driver model together as a larger model and consider this E sub C, which is a combined error term in the lateral displaced mode. In this, we have uncertainty in the driver model, the neural network model, and the uncertainty come from this neural network model parameters, right? The theta vector, and that has uncertainties, right? Different humans are theta going to change for sure, right? Even the same human, today you are in a hurry, tomorrow you are in a relaxed mode, your theta may be different, right? So day to day. So that is uncertainty we want to address. So then we acknowledge this theta is uncertain, then we put this into this nice adaptive control framework. So we are not using this, we are not using the traditional certainty equivalent adaptive control. We actually created this non-certainty equivalent adaptive control. Essentially, we come up with a new approach, right? New adaptation, and also use a projection, use a smooth projection for these unknown parameters, and come up with this Lyapunov function, all right, a little bit different from the equivalence-based adaptive control. We were able to analytically show that the V dot is going to be negative semi-definite. Then we can go through the process. We can guarantee asymptotic convergency of the error with theta being unknown and being uncertain. And we demonstrated in this challenging racing course, right? You can see this course has a lot of very sharp turns, right? Very sharp cornering maneuvers. And in this maneuver, we also let the vehicle speed to vary, right? This is adding another level of challenge, not constant velocity. And we tested 4 drivers, 4 human drivers, right? This one is showing one of them. You can see this is essentially comparing 3 curves, right? Red is when the controller is off, solid dark blue, that is when we're using certainly equivalent adaptive control, and light blue, that is using our own proposed non-CE adaptive controller. You can see the errors, right? The 3 errors, right? In terms of EC, lateral displacement error, heading angle error. You can see the light blue is considerably better than the dark blue. Of course, both of them are better than the red, right? Which has no control. Then we quantitatively compare 4 different drivers, number 1 all the way to number 4, and their root mean square error term, right? When the controller is off, this is already a very big number. Then we use CE adaptive controller, we have much reduction. If we use our NCE, this is the percentage, right? About 30 to 50% reduction of error by the new adaptive control algorithm. So summary, I think we are in a new era, particularly due to the communication and computation advancement. Now, I really want to stress that the multidisciplinary collaboration is becoming necessary, becoming a very vital role in addressing these complex mobility challenges. Bottom line, human acceptance, trust, and adaptability, I think are the most important thing to unlock the potential of all this automation, autonomy technology in their real world applications. So we have additional work ongoing, but I don't have enough published work to form a nice story yet. I hope a couple of years later, I can come back to give you another talk on the other work we have ongoing. So I want to acknowledge my sponsors to my group over the years, and most importantly, my former students and current students, graduate students, who really made those work. Many of them are faculty already, full professors, distinguished professors as well. With that, I want to thank you very much for your attention. Happy to discuss some questions.
Yep.
Really nice presentation. Thank you.
Oh, thank you.
Curious about your driver model and the parameters you've identified. Are they stable in the presence of, say, driver fatigue and changes in visibility?
Yeah, that's a very good question. So in that paper here, you can see what we, the parameter values here. I can bring that slide to be more specific. The answer is no. The model, the factors you mentioned are very important, and they will affect the driver's parameters, even the same driver, right? Fatigue, of course, right? Even mood, right? Today I'm late by 10 minutes, right? Very gonna be impact how I drive, right? So that was part of the reason we started leveraging this neural network as a tool, kind of to describe that, because then we can take this model was in a kind of ideal situation, right? Same conditions, same weather, repeated experiments. But we can borrow the machine learning tool, then can take more factors, weather condition, right? Your calendar, right? Time of the day, right? All this can be better incorporated. We are, again, that's part of our ongoing work. We haven't really published that result yet, but that's absolutely a valid point. Yeah. Akash, yeah.
Great. So, private personal driving behavior has a great market financial value because service which must happen. My question is, how do you ensure
Yeah, that's a very good question. So I can give you 2 aspects. One is that this data, driving data, they are available. Like GM has this OnStar for many years. They have the data. Tesla has everybody's. All these are available already. There's nothing technology cannot do. But privacy, whether human is willing to let somebody to use their data, right? That's a big problem. We just started another project several years ago. It's kind of rooted from your concern, it's a privacy concern, right? So what we did was, okay, it's not exactly that, but it's relevant. What we are addressing was, okay, we're gonna have this different automated system, right? Like automated cars, right? They are made by different companies, made by different, used by different human users, right? So they are heterogeneous. Like, for example, same level 3 car, made by Toyota, made by GM, made by Tesla, they are not gonna share their information or algorithm at all, right? So the provider. Even everything's same, different drivers, right? I don't want to share my driver characteristics with anybody else. So we kind of motivated by that, we come up with another approach right now, ongoing with that. Let's create a universal model. Universal model on which we can represent almost any driver, right? We don't need to use, detailed information. Everybody just transfer some of their key parameters to this universal model. So that way, it's kind of like a bridge. We avoid using their private or this privacy information. We can coordinate at the universal model level. That is kind of addressing that, but not complete. But that's something absolutely not. Yes, you start first.
Can you speak to the interaction between the human learning, like going from the inexperienced driver to the experienced driver?
Yeah.
Right, you're changing the system parameters or the system action. How does that affect, or does that affect how the human learns to control?
Group the skill.
Yes.
Okay.
And like, does it reinforce negative behavior?
Oh, okay.
That kind of-
Yeah, this work didn't consider that, right? It's just, okay, here's the given human skill. How my controller can incorporate that, right? To ensure success. But in terms of human skill growing, or go to the opposite direction, the human may be too over rely on automation, their skill may degrade over time, right? So that's another, I think, again, there are so many different research directions, and all of them are valid and interesting. We can study. That's absolutely good point. You can go either way, right? You can be growing by the machine, or you could be actually degrading your human skills too. Okay, thank you. Oh, okay. So in this setup, I can here, for example, in this setup. So like all the human actions, those are automatically recorded, right? We have steering angle sensors, pedal angle sensors, vehicle dynamic motions, right? Sensors. Those are all captured, recorded here, synchronized. The human's behavior data, biometrics data, like brain activity, EEG image, gaze motion, those are all can be synchronized together as well. So by using this integrated platform, we can collect the data in an efficient way, integrated.
Okay, thank you.
Yeah. Yes.
I have a question about your controller.
Okay.
And your closed loop responses look really impressive.
Yeah.
Now, what was the need to use a nonlinear model and do adaptive control on that rather than using the simple model and just like designing an adaptive robust control?
Oh, you mean the vehicle model? No,
Or the human model?
human model,
Yeah.
vehicle model. Okay. Okay, that's a good question. So you can see the motivation here was looking at this kind of thing. This kind of very challenging course, right? It's racing track. It's in which the vehicle will in the nonlinear region in terms of their dynamics. And the human behavior also become very, very complex. It's no longer ordinary highway. This is a racing track. You can see these sharp turns, right? So we want to capture that. Then we kick into the nonlinear region. For both like tire dynamics, absolutely in almost saturation. It's become nonlinear. The vehicle body, all this motion becoming more and more coupled. And the square terms and all this product terms show up. Human behavior also become very nonlinear. So we no longer can enjoy the linear model.
So then I would assume that you would need a significantly more amount of data to identify the model parameters as compared to the simple model, right?
Yeah, that's another reason we say, okay, let's borrow neural network. See if that can help. So we use the neural network model to train sufficient amount of data to get this result. So that's not an analytical formula, it's just neural network. But the theta of the network vector is uncertain, is unknown actually.
Right.
Yeah, we treat that theta as the parameter to be adaptive, with adaptive control.
That makes sense. Okay, cool. Thank you.
Yes.
Okay, thank you. Question regarding the experiment and the obstacle avoidance and optimization of the drivers, like assistance to the. Yes. Obstacle avoidance, but if like considering the irregularity of something like an obstacle avoidance problem, then wouldn't like some kind of assistance also depending on the obstacle. Oh, yeah, you're talking about the linear avoidance scenarios, could be different, right? That's true. You can have many different scenarios, right? The example we showed here was just one scenario, one of the linear avoidance scenarios, right? When the context of the setup is very different, then the controller may not be sufficient to be working, because in some situations, steering may be not a viable solution, but then the steering doesn't work. Right? So what we just showed, okay, in this limited confined scope, benefit is there.
Thank you for your comment. I have a question about page 31.
Sure. Okay.
Yeah, where you showed with or without control, experienced and inexperienced users show different performance.
Yeah.
I'm just curious on the plots, for the plots on the right, why the three different scenarios eventually converge to the same curve? So for instance, it looks like the red one, the green one, and the dash blue one.
Yeah.
They're from two different drivers. Why do they converge to the same curve?
Yeah, this double lane change maneuver, right?
Oh, I see.
So this yaw rate, right? When
Oh,
you have
I
lateral motion, you have non-zero yaw rate.
I see.
But when you come to the straight line, right? This is already
Oh,
zero.
okay.
But this one is failure. The gray is a failure. Gray is for this one. So it's already lost, already lost the stability, right? The car is spinning, right? So that's why it has this non-zero yaw rate and non-zero lateral acceleration, because it's spinning.
That makes sense.
Yeah.
Thank you all. I have a lot of questions, but I will just ask the general questions for the sake of time. So you showed all this collaboration with the OEMs in the last slide. I'm just curious, are those OEMs buying this concept of personalization? Do they see a clear pathway to capitalize this kind of product? Because I was on the OEM side before I joined Purdue.
Yeah.
It's all about making money, right? How they can make money out of this kind of feature on their vehicles.
Yeah. You can see this kind of papers, for example, were published about 10 years ago, and then some of these. So for example, this one was 2017, okay, about 10 years. So once we publish all these papers, now we suddenly realize, for example, some of the OEMs are actually doing this kind of similar thing like Tesla. They actually, some of the customers notice that the pedal behavior of Tesla is changing over time with your driving history. So whether we didn't collaborate with Tesla, right? So whether our work had any relationship with them, we don't know. But at least I think the industry has some of this personalization. When I talk with for GM, they had a lot of interest in terms of, but actually they are also doing personalization in different ways. Actually, January, I was at the CES, Las Vegas to show the electronic display, consumer electronics. As I noticed, there are a lot of automotive companies, they are, have almost I frequently see the keywords personalization, like showing on their board display. So it's becoming a trend because we have data, we have the computational power, and customers have demands, right? As I said, it's a machine I bought, I paid money, and the machine need to serve me, not serve you, right? Or you bought it, serve you, not serve me, right? So it's a need. Like your computer, like your cell phone, right? You have some space to change. So I think the same is here.
Thank you. Let's thank the speaker one more time. Please all hang around for another 30 minutes or so.
Yeah.
Please feel free to mingle. And thank you very much. Have a great weekend.
Okay. Thank you.